Okay, good morning once again. And I thank the organizers of this summer Harmattan school. So, my name is Orotoye Temitope, a medical physicist at Marcel Cancer Center, Victoria Island, Lagos State. And I won't be the only person taking this class. I have with me Mr. Adewa Dare. Mr. Adewa Dare, are you here?
Yeah. Good morning, everyone. I am Adewa Dari, a medical physicist from Eko Cancer Center, Ikeja, Lagos. I hope you enjoy today's lesson. And please, if you have any question along the line, can just drop it for us on the chat box. I will get to them as soon as possible. Thank you.
Thank you, Dare. So today we'll be talking on this is the outline of our course for today. We'll be talking on how a LINAC work. Then we'll be discussing percentage depth dose, inverse square law, and we'll be taking some exercises. So to know how a LINAC work, and at the end of this virtual lab, we should have understood how a LINAC work, and we should be able to solve some questions. So to understand how a LINAC work, we'll be playing a video now. I want us to please watch with attention. Let us be attentive and follow this video. Thank you.
How the linear accelerator works. All body cells can be damaged or killed by radiation, but tumor cells are more sensitive to radiation than normal cells. Radiation therapy uses this principle to damage beyond repair or kill the abnormal cancer cells in a tumor. Successful radiation therapy depends on the ability of the linear accelerator, or LINAC, to deliver a tumoricidal dose of radiation to the tumor, while ensuring minimal radiation of normal tissue. The LINAC accurately produces, monitors, controls, and conforms the radiation beam to the planned target. Beam generation. Radio frequency waves are pulsed into the waveguide by the magnetron. This is synchronized with the injection of electrons into the waveguide by the electron gun. The radio frequency waves accelerate the electrons along the waveguide to a speed approaching the speed of light. The X-ray beam is created when the electrons hit and interact with a tungsten target at the opposite end. The magnetron controls the power and frequency of the radio frequency waves, which determine the energy of the X-rays produced. The digital accelerator uses a diode-type electron gun situated at the end of the waveguide. The electrons are produced by heating the tungsten filament within the cathode and are then injected into the waveguide. The number of electrons injected is controlled by the temperature of the filament. The electrons are accelerated along the waveguide toward the target. The waveguide contains a series of copper cells. Small holes, or irises, between these copper cells allow the electrons to travel along the waveguide and help to focus the beam. A vacuum is created to ensure that the electron beam is not impeded by other particles. The path of the negatively charged electron beam is controlled by two sets of quadrupole magnets, called steering coils, that surround the waveguide. An additional two sets of focusing coils help to further define the electron beam so that it is very fine, with a diameter similar to that of a pinhead when it hits the target. The entire system is cooled by water. The electrons exit the waveguide and enter the flight tube, where the beam is redirected towards the target. The electrons travel along a slalom path within the flight tube. Three pairs of magnets on either side of the flight tube cause the electron beam to bend through the turns of the slalom. This process not only positions the beam to strike the target, but it also further focuses the beam to a diameter of 1 millimeter. The design of the magnets enables them to focus electrons of slightly different energies onto the same point on the target. This is called achromatic behavior. This slalom bending is unique to electrolinear accelerators. It helps to minimize the size of the machine and ensures that its isocenter remains low, which is important for patient setup. The high-energy electrons hit a small tungsten target where the electron energy is converted into photons, or X-rays. The high-energy photons emerge from the target in a variety of directions. The primary collimator only allows forward-traveling X-rays to pass through, creating a cone-shaped beam. The primary collimator minimizes leakage and therefore excess total body dose by absorbing scattered X-rays traveling in the lateral direction. It also defines the maximum size of the resulting clinical radiation beam. At this stage, the photons are not uniformly distributed across the beam, and so a flattening filter is placed in the path of the beam. The cone-shaped filter absorbs more photons from the center of the beam than from the sides, creating a uniform photon beam. Dose measurement. The photons now pass through the ion chamber for dose measuring and beam quality monitoring. The dose delivered to the patient is measured and controlled simultaneously in two independent ionization chambers. One chamber is the primary dosimeter. It measures the radiation and terminates the beam when the required dose has been delivered. The secondary ion chamber acts as a backup and will stop the irradiation if the primary chamber fails. The treatment machine must replicate the beams modeled within the planning system. This is critical to the accuracy of treatment delivery. A beam quality function is performed by a third ionization chamber, which uses 7 electrodes to monitor different sections of the radiation field. The X-ray beam is almost ready to treat the patient. Before that, further beam shaping is required to ensure that the shape of the delivered X-ray beam matches the shape of the tumor. This is done using a multi-leaf collimator, a number of fine tungsten leaves which move independently of one another and can create a variety of complex treatment shapes. LINAC control. One computer system controls both the LINAC and the multi-leaf collimator. This eliminates dosimetric errors due to communication delays. It also ensures synchronization between the delivered dose and the multi-leaf collimator position, allowing complex deliveries such as intensity-modulated radiation therapy and volumetric modulated arc therapy. All electromagnets, steering, and focusing coils are digitally controlled. All mechanical positions of flight tube, filters, and foils are automatically selected from the control console, and all radiation beam settings are grouped in calibration blocks for each energy. These are stored digitally on the LINAC hard disk for flexible and easy beam adjustment, calibration, and servicing. Clearance. Clearance is the free space available under the LINAC for patient treatment, and it varies with different protocols and fixation devices. It is a combination of the distance between the lower surface of the radiation head and the isocenter, 45 centimeters, and the head diameter, 62 centimeters. A wide clearance around the isocenter means improved access for patient setup, freedom to use the best possible patient positioning and immobilization accessories, freedom to rotate the gantry between fields without needing to move the patient. Finally, it means that treatment techniques using non-coplanar beams are not compromised. The large clearance offered by Elekta machines ensures flexibility in providing the best possible treatment for the patient. How the linear
Okay, thank you. Now we have a question from the video we just watched. What are the functions of ionization chamber and flattening filter in a linear accelerator? The functions of the ionization chamber and flattening filter in a LINAC. So please note this question. At the end of this class, we'll come back to it. Okay, so briefly, I want to talk about beam data measurement. Now we just saw a video on a linear accelerator, which is a machine that is used during external beam radiation therapy to deliver radiation dose to patients. Now, when you acquire a linear accelerator, you just don't start using it for treatment. There are some other tests and measurements that you have to carry out. And one of the equipment that is used in carrying out this is what is called a water phantom. This is a 3D water phantom. A 3D water phantom is used in beam data measurement. Now, when a linear accelerator is acquired, we do what is called acceptance testing and commissioning. That is one of the core functions of a medical physicist, and no other professional can actually do that in a radiation center, but it is the major work of a medical physicist. Now, a 3D water phantom is placed, as you can see in this picture, it is placed on the machine. Then we use ionization chamber. Ionization chamber is placed at several depths. Then it is exposed to ionizing radiation of several energies, because in a machine, you can have, in a linear accelerator, you can have energy ranging from 4 megavoltage to 25 megavoltage. Now, the 3D water phantom will be exposed. The reason why we use a 3D water phantom is because we use a 3D water phantom is because it is tissue equivalent. You can't just pick a human being and be using it to test some parameters. This is radiation we are using, and we all know that yes, it is used for treatment, but it is also dangerous. So that is why a 3D water phantom is used. We acquire some results, and that is what is used to do beam correction. We use it to test whether the parameters, everything in the machine is functioning properly before you can say that, okay, the machine should be used to treat patients. So I would like to talk briefly about percentage depth dose. In fact, this percentage depth dose is very important when radiation therapy is concerned. Not only radiation therapy, but where radiation is used, it is very, very important. Now, what is percentage depth dose? Just as we can see here, it has to do with percentage depth and dose. So it tells us about the percentage of absorbed dose in a tissue at various depths. The percentage of, so it is defined as the quotient of percentage of absorbed dose at a particular depth to absorb those at a reference depth. There's something we call Dmax, which is this reference depth for different energies. For different energies, we have different Dmax for different energies. For a cobalt 60 machine, it is 0.5 centimeter. For a 4 megavoltage energy beam, it is 1 centimeter. For 10 megavoltage energy beam, it is 2.5. Then when it has to do with 25 megavoltage photon beam, it is 5 centimeter. So several energies have different Dmax. So percentage depth dose tells us of the percentage of the absorbed dose that is absorbed in a tissue at different depths in reference to the absorbed dose at the Dmax that I just listed. Now, the percentage I'm back. Sorry for that. I hope I'm still sharing my screen. Okay. Okay. So, like I said earlier, when there is an increase in energy, there is also an increase in percentage debtors. And when the feed size increases, there is also an increase in percentage debtors. This is because there will be an increase in scatter of the radiation dose. And as the tissue, as the depth increases, the percentage debtors decreases. Then when there is an increase in SSD, that is the skin to surface distance, there is also an increase, a negligible increase, an increase also in percentage debtors. This is because of inverse Squalor, which I'll be talking on shortly. Okay, so inverse Squalor, this is a very important parameter that we, as far as radiation is concerned, you have to talk about inverse Squalor. So it tells us about the intensity of radiation. So like as you move away from a source, from an isotropic point source, then as you move away, then it is expected that the intensity of the radiation dose that the person or tissue is exposed to, the intensity will reduce. So because, radiation is given in quanta, and that is just talking about the intensity, it has to talk about the amount, the number. So the number of quanta in a particular area, that is what is known as the intensity of an X radiation or of a radiation. So the law states that radiation intensity from a point source is inversely proportional to the square of the distance away from the radiation source. I'd like to use these to Okay, looking at this particular slide, this is the formula for inverse Squalor. High 1 divided by high 2 equals squared of the final distance divided by squared of the initial distance. Now, looking at this particular image, we have a point source here. This is a radiation point source. Now, as the distance is increasing, we have as the distance is increasing from the source, the radiation dose, like you can see from here, when for here that it is 1, let's assume that it is 1, it will be inversely proportional to the square of the distance. When it is 2 centimeters, then the radiation dose is expected to be 1/4 because that will be 1/2 squared. And when it is at 3 centimeter and on like that. So as you move away from a point source, it is expected that the radiation will be inversely proportional to the square of that distance. So from this, we would like to have some questions that we'll take now, and on percentage depth dose and the inverse Squalor itself. Don't forget the formula for percentage depth dose is dose at depth all over D max multiplied by 100%. And this is the formula for inverse Squalor. High 1 over high 2, which is the initial intensity, all over final intensity, equals to squared of the initial distance all over squared of the final distance. Sorry, I mean squared of the final distance all over squared of initial distance. Yes. So you have 2 minutes each for each of this question, and after everybody is expected to solve this question. Then after, we have 6 questions in total. So in the next 10 minutes, we'll be expected to submit our question. You can put your questions in the chat box, then we solve the questions together.
All right. Thank you, Tokwe. Well done. A nice presentation. Please, we need to be very, very fast because we have just like less than 15 minutes to leave this section. So, and we have 6 questions, 5 questions on PDD and Neva Square Law. And the last question on LINAC, that is, what are the functions of ionization chamber and the flattening filter? And mind you, on the ionization chamber, we have 2 types as seen in that video. We have the primary and the secondary. So now you have to like send your answers like the functions of the primary and the function of the secondary ionization chamber. So now we have just 2 minutes. And if you have any issue on a particular question, please send your question via the chat box and we'll respond immediately. So now you have 2 minutes per question. So we'll just go through the first one. Now, it says the intensity at 100 centimeter is 200 centigrade. What is the intensity at 50 centimeter? So now here, this is a question under inverse square law. So use the formula as you have seen from the presentation. Then you send in your answer. Your time starts now. Now that is the formula on the screen, that intensity like high 1 over high 2 equals d2 square over d1 square. High is the intensity, that is the amount of energy deposited or the strength of energy, from the radiation source. And this is the distance. So please send your answers via the chat box, your question, everything, and thereafter we'll do correction. You mark yourself and we explain. Thank you. Uh, 30 seconds more. 30 seconds more. 30 seconds more. 20 seconds. 15 seconds. 10 seconds more. 5 seconds. 4, 3, 2, 1, 0. Thank you. The second question, please. Now, it says a cobalt 60 source gives a gamma dose rate of 160 microsievert per hour at 1 meter away. At what distance would the dose rate be 40 microsievert per hour? Like we are still using the inverse square law equation. So you have your intensity and you have your distance. So that's the formula again. "45 seconds more. 45 seconds more. 30 seconds. 20 seconds. 10 seconds. 5 seconds. All right. Thank you very much. The third question. The third one. Now this is on PDD, percentage depth dose. Now find the PDD for a 15 by 15 feet size and depth 1 centimeter for a 100 centimeter source to surface distance. Now the source, like the X-ray source, now to the surface of the water phantom or to the patient surface, like that is the SSD. So now we have 100 centimeter SSD. Now we want to find the PDD. Now we have the depth at 1 centimeter. Now our D max is is assumed to be 1.5. So now that is the formula for our PDD. That's PDD equals to dose at depth over those at reference depth, that is maximum depth, that D over D max, multiplied by 100%. So let's use this formula quickly and get our PDD. That one, you have just 30 seconds. 30 seconds. Sorry to the question. Back to the question. 10 seconds more. 5 seconds. 2 seconds. 1 second. All right, thank you. Now the fourth question. Our time is running. Please, you have to speed up. Now, this is on inverse square law again. Now, the intensity of radiation from a radioactive source is 900 milliroentgen at a distance 20 meters. At what distance will the intensity of radiation be reduced to 6.25 milliroentgen? Now, the hint there is that use the inverse square law formula. I hope we still remember the inverse square law formula. That's I1 over I2 equals to D2 square over D1 square. So fix in your parameters and just send in your answers. We have for just 30 seconds. 30 seconds. 30 seconds. 20 seconds. 900 milliroentgen is the first intensity. The first distance is 20 meters. Then you are looking for the second distance, and with an intensity, the second one of 6.25. Please send your answers on your number 4 answer. All right, thank you. Let us move to the fifth question. Now this is on PDD, so I expect us to use like 5 seconds to solve this one. If the PDD of a cobalt 60 beam at 2 centimeter depth in the wire phantom for a 10 by 10 centimeter square, that is the fit size, is 94.3% at 100 cm SSD, that is source to surface distance. Now, Now this is the question. The PDD at 3.5 cm depth in wire phantom. Now that water phantom we saw earlier in the presentation. Now, assuming you are seeing the phantom now and you are doing like a real-time measurement. Now, the PDD at 3.5 cm depth in water for the same fit size and SSD. That is the same fit size 10 by 10 and the same SSD 100 centimeter. Now we take our D max to be 4 centimeter. What is the PDD? We have just 5 seconds. We are still using the PDD formula. Now, after we'll do the correction and you mark yourself. So that's the formula there. Okay, now this is the question. So we should be true now. We should be true. All right, thank you very much. Now, so we'll take the solution now. And if you have any question, please do well to send to us through the chat box. Now, from the video, what are the functions of ionization chamber and flattening filter? I said that from the video you saw, we have 2 types of chambers. We have the primary and the secondary. So now you have to tell us the function of each of them and the function of flattening filter. So this one we have just let's say just 10 seconds. Just a short answer. Please don't forget, if you have any difficulty, just send it through the chat box and we will get back to you. All right, thank you very much. Thank you. So let's take the correction. So you can mark yourself now if you are right or not, you will know. Now, please talk, let's see the solutions. Thank you. Now, the first one. The first one, you remember that it was a question on inverse square law, and this is the formula. That's the first intensity, that's the initial one over the final one, equals to the final distance all square over the initial distance all square. And from the question, we can see that the high one is a 200 centigrade and the D. So now you insert all these values into the above inverse square law formula. I think this is simple enough for us to grab on time. So now the high one is 200, and the high two is unknown, so we represent that as y equals to the d2. Now we have 50 centimeter, that's all square, and d1, that's 100 square. So now 50 square, that is 50 multiplied by 50. 50 in two places, we have 2005, and 100 square means 100 in two places, that's 10,000. So we then cross multiply, then we have our answer. We have 800. So now if your final answer is 800, then you should mark yourself right, but otherwise you should mark yourself wrong and take the correction down, case of next time. Thank you. So number two, the same formula, the same procedure, just that we need to look for our final distance. Now we have our values here, 160 microsievert per hour. That is our dose rate, that is dose over time. You know, this microsievert over hour, that's an hour is time, that's dose rate. Now, and our D1 is 1 meter, I2. So, and now these are the so now you insert all these values back to the formula, then we solve together. So 160 over 40 equals to a square over over 1 square is 1 times 1, and that's 1, so we cross multiply, then a square. Now 60 multiplied by 1 over 40 should be 4, so that's a. Now that the square root of 4, so we have 2 meter. So if your final answer is 2 meter, then you should mark yourself right, and if otherwise, please take down the correction case of next time. Thank you. The third one, now this is on PDD. So now the formula you saw from the screen during the presentation, now we have the depth those at depth D over those at maximum dose as a reference dose. Now with respect to the energy used, like cobalt, we have 0.5, 4 MV, and we have 1, and all those things. Now what our presenter explained that time. So now here D is 1 and D max is 1.5. So now 1 over 1.5 now multiply by 100. So you should get 67%. So if your answer is different from this, please you should take down this correction. So you can see all those questions are very, very simple. And the fourth one is on inverse square law. So it is the same thing. That's I1 is 900 milliroot gene. Root gene, yeah, milliroot gene, and D is 20 meter, I is 6.5 milliroot gene. Root gene is used to measure exposure, yeah, and meter for distance. So now these are your values. So we insert all those values back into this formula, and we then cross multiply, and the square root of 57600, that is 240 meters. So now if your final answer is different from 240 meter, then you should take down the correction, and you can redo it. Now to the fifth one, now is on PDD again, and that the same formula. Our dose at this step is 3.5, and those at D max is 4.0 cm. So you insert all this into the formula, and if your answer is 87.4%, then congrats, you should do well to try more questions, like can go through Pogusac or can textbooks, and lay your hand on more questions. Now, the 61, I was saying that during the video we saw, two chambers were mentioned. We have the primary and the secondary, and the primary chamber measures the dose to the chamber, and terminate dose once the required dose is deposited or delivered in the tissue or let's say biological tissue or in the phantom. Now, at the secondary, now it functions as a backup in case of error or in case of malfunction of the main chamber. So now here the primary chamber is actually the main chamber, or let's say the major chamber that works. So now, and it measures those, like, and that we can read it. In that 3D phantom, during measurement, you just place your chamber and you expose, or let's say you beam on, and after a while, maybe a minute, 2 minutes, then you check your electrometer, and the value you see on the electrometer is the measured dose from the gantry, from the machine. So, the secondary one act as a backup in case the main chamber, that is the primary chamber, malfunctions. All right, now to the flattening filter now. Now, when the machine produces electron and it hits a tungsten target, now it turns to a photon beam, and that photon beam happen to be non-uniform. And now, to treat cancer, we need a more uniform beam, so that we not have one side like with a less dose and the other side with more dose. So we place a flattening filter on the part of the photon beam. Now, and what it does is that it will create a uniform photon beam, and at times it absorb, like, we will say soft S3 or weak S3. Now, so now to have a what to kind of so when you have what a more uniform photon beam. So I think that's all for now. Please, if you have any question, I will advise us to just see the video at our Leo, because a link should be sent to us. So at your Leo, go through the questions again, go through the video again, and if you understand what is in the video, then you are on your way to becoming a clinical medical physicist. So if you have any question, we are still waiting for our questions. Please just send them via the chat box, and we will answer. Thank you very much, and I hope you have learned a lot. And if you have any further question, I can get back to the organizer of this Harmattan School, Dr. Your poster, and just send her a mail, and every question shall be duly answered. Thank you very much. That will be all from my side. Any question? Okay, let me check our answers. Okay, just send in what you score. Like we have six questions. Just like if you score 5, just write 5 of 6. Now, if you score 1, just write 1 of 6. And if you score the whole 6, write 6 of 6. And if you score 0, just write 0 of 6. Now I can see some 3 of 6, 4 of 6. That's good. 2 of 6. You should take down all the corrections and work on yourself more. Okay, 5 of 6. That's good. That's brilliant. 1 of 6. Wow. So you should go over the question again. A link shall be sent to you. So at your Leo, go back to the question and try them again. Now 4 of 6. Okay. 5 of 6. 4 of 6. 2 of 6. All right. All right. 2 of 6. 2 of 6. 2 of 6. Wow. We have a lot of 2 of 6. What happened? They are simple question. 2 of 6. 3.5 of 6. 2 of 6. Okay, this one said he didn't start from the beginning. That was why he scored 2 of 6. All right. So you should go through the link and start all over again on your own. All right. 3 of 6. 3 of 6. All right. All right. That is beautiful. 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 All right. Thank you. That will be all from our side. Thank you, Tope, for the presentation. And I would like to acknowledge Electa for the video. Thank you, Electa, and Eco Hospital for the 3D water Phantom and the fourth and the machine. Thank you very much. And IPEM as well. Thank you very much. And Dr. Yobosa and the rest of the team. Thank you. God bless you. Bye for now.